Hi everyone, we move on to section 3.6. This section and the next are our first heavier applications of derivatives. So 3.6, this is related rates. This is about as heavy as the applications will get. So we'll see several applications in later sections as well. Most students feel that related rates is quite challenging. So I'd like to say that at the beginning, just so that as you're doing the work, expect these to come slowly. And that is very normal, but push through it because it's definitely something that you can attain a high level of achievement, but it takes some time. Okay, so related rates is an application of implicit differentiation. So I'd like to start by reviewing that, and there's actually a little bit of a twist on the implicit differentiation that we'll see with related rates, and we'll even explain where this name comes from. Okay, so here we go. Let's start with this quick example. This is implicit differentiation. Take the derivative of both sides with respect to x. So these are the sort of things that we did in 3.5. So let's say, okay, if we've got x squared plus y squared equals 25, then to take the derivative of both sides with respect to x, you might first apply a d over dx with brackets to the left side and then also to the right side. And of course that means we're about to take the derivative of what is inside the brackets. So now let's go ahead and execute that. And you may remember, okay, the derivative of x squared with respect to x, if they're the same variable, it's just a normal derivative. So here 2x. But if you're taking the derivative of y squared with respect to x, they're different variables. So you'll take it as normal at first, 2y, but then remember to attach a dy over dx on the end. And we went through all the theory there that accounts for the chain rule. Okay, at the end of the day, just remember, take the derivative. If the variables are different, take the derivative as normal and then attach, in this case, a dy over dx. And the right side, the derivative of a constant, well, that is 0. Okay, so what's it going to look like then when we get into this section? Let's still work with x squared plus y squared equals 25. But we will take the derivative of both sides with respect to a new variable, a third variable, t. So what is that going to look like? Okay, well, you might start with a familiar first step, but now if it's a derivative of both sides with respect to t, then you would write d over dt for the left side equals d over dt for the right side. How's this going to play out? What does that mean? Okay, so notice neither x nor y match that new variable t, right? They're all different. So when we take the derivative of x squared with respect to t, well, the variables are different. So we have the 2x, but then we multiply by dx over dt. And there's your derivative of x squared with respect to t. Plus y squared, well, that derivative is 2y times dy over dt. Because again, the variables are different. And it equals, well, in this case, it doesn't matter what the variable is, the derivative of a constant is 0. So we've got kind of the next level of implicit differentiation that we'll need to use in this section. And we can explain the name related rates at this point. So notice this equation here involves two derivatives, the derivative of x with respect to t and the derivative of y with respect to t. So when we have two derivatives inside of an equation, it tells us, well, these are related rates, right? Derivatives represent a rate of change, an instantaneous rate of change. So there's a rate of change, there's a rate of change. They're connected in this equation, so we can see how those two rates are related to one another, and we literally have related rates. This one tells us how x is changing, this one how y is changing. There you go. We're going to take it one more step, and I'll just show you this last part here as well to get us more familiar. We ease into these problems. Once we have an equation like this that involves, say, two rates, we'll look at situations like this. What is the value of dy over dt when x equals 3, y equals 1, and dx over dt equals 1/2? So just kind of pretend for a moment that somehow we know these values of x, y, and the value of dx over dt, and we'd like to know the value of dy over dt. So we'd like to know this, but we're told x, dx over dt, and y. Well, we can just plug all those in. So we'll plug. So we got 2 times, and we'll plug in the x is 3, dx over dt is 1/2, plus 2 times y we were told is 1, and we'd like to know the value of dy over dt. Bring this in a little closer. You think, okay, well, that's just gonna, we treat dy over dt and dx over dt just like they're a constant, right? That they have, not a constant, like a variable. They could be assigned a value. That entire thing can be assigned one value. So now we want to know the value of dy over dt. Okay, no problem, right? We can go to the next page, apparently. So start with that. We can simplify a little bit. So we got 2 times 3 times 1/2. Well, the 2 and the 1/2 cancel, so we just have 3, and the 2 times 1, okay. And we can very quickly realize, all right, after we simplify, subtract the 3 just like you normally would, divide by 2, and dy over dt in this case equals -3 over 2. So we're solving for it like it's any other variable that you might see. All right, we are ready. Let's dive in to a beginner related rates problem, and we'll see all of this, how it all comes together with these concepts. This is about as simple as they get. None of them are simple, but this is as simple as they could be. A rock is thrown into a pond, creating a circular ripple. So we probably all know what's going on here, right? Throw an object into still water, and it creates a big circular ripple that expands. If the radius of the ripple increases at 5 feet per second, how fast is the area of the circle changing when the radius is 20 feet? Okay, so let's think about that for a second. When you throw an object into still water, the radius will expand at a constant rate. So in this case, they're telling us 5 feet per second. Now that's pretty fast. So this rock must have hit pretty hard. 5 feet per second, okay. But what does that tell us about the area of the circle that is created? Would the area of the circle be growing at a constant rate? And I'll just do a quick drawing here, and we'll know, right? So let's say, you threw that rock, kind of at the center there, and now the radius is expanding. So let's say maybe 1 second later, now the radius is out to here. So if I draw that circle, right, the area, got a little funky over here, that area grew a lot, right? Say 1 second later, there's the new area. All right, so that area really, what about a second after that? So I'm going to try and make the radius increase by the same amount, trying. Did the area increase by the same amount? at first it increased by this, but now the area has increased all of this, and I think we can all agree the area of this outer portion is a lot bigger than the area of this inner portion, although the radius grew by the same. So even though the radius is increasing at a constant rate, 5 feet per second, the area is actually growing faster and faster and faster. The further out it gets, the more area it attains every second, let's say. So the question is, how fast is the area of the circle changing when the radius is 20 feet? So we're thinking at exactly a 20-foot radius, how fast is the area growing? Okay, so here's what we need. We need an equation to start us off. They don't give us an equation, but they give us enough hints at what we're going to use. So they talk about area, they talk about radius, it's all a circle, right? Do you guys remember the formula for the area of a circle? Well, I know you can't answer me, so I'll just tell you. It's area equals pi r squared, the area of a circle. Okay. So that's where we'll begin. What are we going to do with that formula for the area of a circle? Well, we're going to think of it like an equation which has two variables. It has r and it has a. So we're going to take the derivative of both sides with respect to t. Here's what that will look like. I'm going to lay out all of the steps once this example is done. And so you'll see what I'm saying in words written out again. But okay, what did we do? We had our equation with two variables. We take the derivative of both sides with respect to t. Normally we use x and y. Here it's r and a. Okay, no big deal. So the derivative of a with respect to t, well, there's not really much here. It's simply dA over dt. However, on the right side, when we take the derivative with respect to t, we take it like in the normal way first, right? So the 2 multiplies down. The 2 would multiply by the pi, in fact, and then it would drop to a first power. So 2 pi r to the first. And then we attach a dr over dt to the end, the derivative with respect to t. So now we have a related rates equation. We know how fast the area is changing here, d over dt. The dr over dt represents how fast the radius is changing, and r is simply the radius at that moment. Okay, so once we get this equation, we want to go back to the question and think, all right, which one of the rates are they asking us to find in the end? Okay. Are they asking for dr over dt, or are they asking for dA over dt? And if we read the question right there, how fast is the area of the circle changing? This is what we're after. We're trying to find the value of dA over dt to answer the question. So that must mean that they tell us the values of the other two. They must tell us r, and they tell us dr over dt. And they do, right? So that, at the first number they give us, the radius of the ripple increases at 5 feet per second. That's how fast the radius is changing. 5 is dr over dt. And then they say, how fast the area is changing when the radius is 20 feet. So we'll plug in 20 for r. What is dA over dt when r equals 20 and dr over dt equals 5? So we're going to plug those right in. dA over dt equals 2 pi times 20 times 5. And we can simplify that. I went ahead and left pi in the answer. But it'd be perfectly okay to multiply 200 by 3.14, let's say. If you want to answer that way as a decimal, that's not a big deal. But in the end, there it is. dA over dt equals 200 pi. And if you're wondering what the units would be, it turns out they're feet squared over seconds. Why is that? How does that make sense? How could we figure that out? Let's talk about how we would figure out that these are the units. It's literally what you see here. Area units divided by, and you probably maybe have figured out what T represents. It's time. So the area is feet squared divided by, and here the time is seconds, is the way the problem describes it. So there you go. Area over time, feet squared per second. And that makes sense, right? How fast is the area growing? Well, you're gaining feet squared, and it's happening every second. So at the moment, the radius is 20 feet. Right at that instant, the area is growing by 200 pi. That's a lot of feet squared per second. That is really fast. Okay. We're going to conclude with my related rate steps. We're going to conclude this video. And we'll kind of go back and highlight where these steps occurred in our problem. So step number 1 is to make a drawing. Now, in the problem we just did, the drawing that I made at the beginning, you saw my yellow paper here, that's really not what I'm talking about. This was helpful to get an idea of just what's going on kind of, within the problem. But typically the drawing's not going to, take this sort of a form where we're kind of drawing and drawing again and kind of looking. We'll see examples coming up soon where the drawing, has a much more important, much more impactful presence in the problem. The truth is, in the problem we just did, we really started with number 2, find an equation relating the quantities. So this is what we were after. A equals pi r squared. You could argue all of my drawing really wasn't even necessary in this problem, because once we had that equation, well, then we can take the derivative of both sides, then we can plug in and we can answer it. So I've got this asterisk next to number 2 for a couple reasons. For one, the whole point of making the drawing is so that you can find the equation relating the quantities. Here the quantities were radius and area. So sometimes, like in this last problem, that drawing really wasn't necessary, so we can skip that and go right to the equation. In other problems, it will be essential. We need a very well thought out drawing in order to find an equation, and we'll see a couple examples coming up. Okay, once you have that equation, then it's time for step 3. Take the derivative of both sides with respect to t. And we use t because it is always going to represent time. All right, once we have that derivative with respect to t, then step 4, find the unknown rate by plugging in known quantities. So for us, we wanted to identify the unknown rate that we're looking for is d over dt. So that must mean we can plug in for the other quantities, the r and the dr over dt. And so we did that here, and then we were able to very quickly solve. So the truth is, when you're looking at these steps, a lot of times, step number 2, the other reason for the asterisk, this is the most difficult step. It's very common to just setting up the equation in the first place is more than half of the work. Because once you have that equation, hopefully by now you feel comfortable taking derivatives of all different types. And then once you have the derivatives, it's just a matter of plugging numbers in and then solving. And there can be some trickiness to, there's kind of some nuances to plugging these numbers in that we'll see. We're going to get a little bit harder, but really it's that equation. Once you really can't do anything until you have that equation. Once you have that equation, then derivative, plug in some numbers, and you can wrap it up. But yeah, that one is typically very difficult. And in this problem, it was, if you knew that formula, then it was immediate, right? There wasn't much work to that at all, if you knew the formula, of course. Okay, let's stop this video here. More examples in a moment.